So good afternoon to all of you. So till now whatever we have done the flow, we have done simple, and first I have given you an introduction and then we have discussed the different flow patterns which are available, and after that I have discussed some very simple analytical models. Now among the analytical models for mixed flow patterns or for well dispersed flow patterns, we have discussed the homogeneous flow theory, and then I have said that when there is a relative motion between the phases, which is a quite common occurrence, and under very rare circumstances, only at very high phase velocities only, we find that the two phases are so intimately mixed that they behave as a single pseudo fluid and the homogeneous flow conditions apply. Under most of the conditions, even when the two phases are well mixed together, there is a relative motion between the two phases. Why? Because the lighter phase will naturally try to travel faster than the heavier phase. So, therefore, there is a slip, and under such conditions we often have to correct or modify the homogeneous flow theory by incorporating the drift flux model. On the other hand, the other extreme was the separated flow model. There what we found, that it was mainly there for flow patterns where the two phases occupy separate cross sections of the tube. For example, the annular flow pattern and the stratified flow pattern are ideal examples of the separated flow pattern. So, under that condition we found that the two fluid model is very applicable, where the two phases are considered separately and separate mass, momentum and energy equations are written for them, and then they are solved by considering suitable interactions between the interface. For simplified matters, we can ignore the interfacial interactions and we can use several empirical correlations to find out the two phase pressure drop, where we assume that the two phase pressure drop primarily comprises of the frictional component, or in other words the two phase pressure drop, it is primarily it is we are trying to find it out for horizontal pipes under conditions where the acceleration and the gravitational pressure drops are negligible. So, after completing the analysis of the homogeneous flow model, the drift flux model as well as the separated flow model, now we would like to take up specific flow patterns, apply the simple analytical models and see how we obtain the, or rather how we analyze the specific flow patterns. Now, since I do not have much classes after this, maybe I will be able to give at most 3 classes to the specific flow patterns, then you will be doing boiling condensation, a good amount of it, and after that we will be doing the measurement techniques and instrumentation. So, since I do not have much classes, I will be trying to cover the analysis for bubbly flow patterns and the slug flow pattern. Slug flow pattern I will do because it is a very unique flow pattern, it has got a periodic flow phenomena. So, this analysis is slightly difficult. Well, the other thing, the bubbly flow pattern I will take up because it is an ideal case of a mixed flow pattern. I would also like to take up the annular flow pattern, but in that case even if I do not have time, I will leave it for the for your analysis part, or rather for your self study part. You please go through it, apply the two fluid model there, and accordingly you can analyze the annular flow pattern. Okay. Now, let us take up the bubbly flow pattern. Now, for the bubbly flow pattern, what have we observed? It is basically, it has got a continuous liquid film, a continuous liquid phase, I am sorry, continuous liquid phase with bubbles dispersed in it. Now, this is the ideal most case where very small bubbles are dispersed. This occurs at high mixture velocity, other high phase velocities. Otherwise, we usually do not get such a situation. We find that we have a liquid phase where bubbles of different sizes and shapes are dispersed. Now, these sizes and shapes of the bubble, they basically depend, maybe we have different sort of bubbles and the sizes and shapes are primarily governed by their by the volume of the air which we have injected, by the relative proportion of the two phases. Now, we find that in both the distributions the it is characterized by a continuous liquid phase where the dispersed phase is the gas phase, but the dispersed phase can take on a variety of shapes and sizes, and in the limit we find that gradually as we keep on increasing the gas velocity, finally we find that these bubbles they coalesce and they form such type of Taylor bubbles and liquid slugs where we get the slug flow pattern. Now, it is quite evident that the analysis which will be applicable here may not be applicable here also. So, more or less we will be discussing the unified approach and then we will be seeing how the analysis takes into account the different shapes and sizes of the bubbles in the different extreme cases. Okay. Now, suppose in this particular bubbly flow. Now, what we know, when the bubbles are uniformly dispersed as I have shown in this particular picture, under such condition we very well know that the homogeneous flow theory is applicable. When the homogeneous flow theory is applicable, we know that alpha equals to beta, or in other words u1 equals to u2 equals to j, isn't it? Under such circumstances, what do we know? We know that your tau w, it is given this can be obtained, or rather we can write it in terms of F two phase, the two phase friction factor, that can be written in terms of tau w by G j by 2. Okay. Under such circumstances we can find it out. Then if we plot this FTP as a function of RETP, or rather FTP if we plot as a function of RETP, then in that case we can find out FTP and accordingly we can find out the frictional pressure drop under these conditions. Now, one thing we know that at low values of alpha, for low values of alpha, we know that the only hitch of finding out RETP is to find out mu Tp. Now, for low values of alpha, we know when the flow this laminar, when bubbly mixture in laminar flow behaves Newtonian. So, at low values of alpha, when bubbly mixture in laminar flow behaves in a Newtonian fashion, under that condition we know mu Tp it can be written down as mu L or mu 1 into 1 plus alpha. And for contaminated liquids, of course, for contaminated liquids we find out that the influence of alpha, it enhances the tendency of the bubbles to behave as solid spheres. Okay. So, therefore, when the value of alpha is very low, we find that the bubbly mixture it is in laminar flow, it behaves Newtonian fluid. Under such conditions mu Tp can be written in this particular expression. And when the liquid is contaminated, influence of, for contaminated liquids, influence of alpha enhanced due to bubble tendency to behave as solid spheres. Why does it happen? It happens because whenever there is some contaminations, the contaminations tend to deposit on the interface between the gas and the liquid. Interface is nothing but the bubble surface. So, therefore, once the bubble surface becomes contaminated, it starts behaving as solid spheres. Okay. So, under that condition, of course, we cannot say that the bubbly mixture is in laminar flow, and under that conditions the mixture it exhibits non-Newtonian behavior. It can exhibit a yield stress, or it shows different non-Newtonian behaviors. It can exhibit a yield stress, it can exhibit a decreasing apparent viscosity with increasing shear rate, it can also exhibit certain other electrical effects and so on and so forth. Okay. So, therefore, under such circumstances we cannot use mu Tp. For turbulent flow, usually when happens when the liquid is contaminated, the bubble concentration is very high. So, for turbulent flow usually FTP can be taken as a constant value of 0.005. This is a good approximation. Now, we find that whenever we have to find out the pressure gradient for this particular bubbly flow case, the pressure gradient, as you already know, this is a summation of 3 components. This we have discussed several times. You already know it is a summation of the frictional component, the acceleration component as well as the gravitational component. For horizontal flow, we know that the gravitational component becomes equal to 0. Okay. Now, for the frictional and the acceleration components. Okay. Now, we find that usually the frictional and the acceleration components, they are important at high phase velocities. Whenever the relative velocity is higher, the wall shear stress becomes more important. Therefore, the momentum flux effect as well as your wall shear stress effects, they become much more important for high flow velocities. Fortunately, under that condition, the flow exhibits homogeneous flow characteristics. So, when your wall shear stress becomes important, when the momentum flux becomes important, under that circumstance we find that the homogeneous flow theory is applicable. Now, at low phase velocities, when the relative motion of the two phases become important, or the gas or it is important to consider the relative rise of the gas bubbles with respect to the surrounding liquid phases, or in other words, when the drift flux model has to be applied, we find that the wall shear stress as well as the momentum flux influences, they are not so very important. Okay. So, therefore, the bubbly flow pattern, the analysis can be divided into 2 parts. One is at high phase velocities, where we can use the homogeneous flow model. This is applicable when the liquid flows at a high velocity and the bubble is dispersed as very fine dispersions in the liquid phase, just as I have shown in the first figure here in this particular case. Now, as we come down to lower and lower phase velocities, naturally the bubble sizes increases. As the bubble size increases, they get more deformed and they take a variety of shapes, starting from spherical, spheroidal, oblate spheroids, cap shapes and so on and so forth. Now, when this happens, the bubble definitely has a relative motion with respect to the liquid, and under such circumstances homogeneous flow model is going to be erroneous. Under such circumstances, we apply the drift flux model. What does the drift flux model do? We have already discussed the drift flux model. It modifies the expression of all the parameters starting from alpha, u1, u2 and momentum flux, kinetic energy, etc., by incorporating the relative motion between the phases or by incorporating the drift flux between the phases. Now, we have already deduced that alpha from homogeneous flow model, it is J2 by J. Okay. This is applicable for the at high phase velocities. Now, moment the phase velocities become less, this becomes J2 minus J21 by J, isn't it? This we get from the drift flux model. So, moment the relative velocity becomes important, this is incorporated as J21 in the model. This we have already done. Similarly, if we take a 1 minus alpha, this is nothing but equal to J1 plus J21 by J. Okay. Same way we had already discussed, I will just write down the expressions. U1 it was obtained as J by 1 plus J21 by J1. These derivations I believe we have already done. U2 was 1 minus J21 by J2, and accordingly we had already derived momentum fluxes and things like that. Okay. Now, we find that whenever we are operating at not very high velocities, alpha has to be modified. Moment we are modify alpha, we can modify rho Tp, we can modify u1, u2 and so on and so forth. Now, for alpha, in order to find out alpha, when the relative motion is important, what is the parameter that we have to find out? The parameter which is not an input, but has to be determined is J21, J1, J, all those things we can already find out from input parameters. So, therefore, if relative motion is important, then naturally J21 becomes important and we need to find out J21. We had already find out that when wall shear stresses, for negligible wall shear stresses, and momentum flux, this we had already derived. We found out that J21 can be expressed as a unique function of alpha as well as the two other parameters. One was u infinity, which is the bubble rise in an infinite medium, and the other was n, which incorporates the effect of void fraction on relative motion. Remember this, I had already told you while studying the drift flux model that more or less J21 it can be expressed, or the curve of J21 can be approximated by this particular equation for a wide variety of fluid pairs, fluid properties, etc., where for the different flow situations u infinity and n take different values. Okay. So, this was the velocity of dispersed phase in infinite medium, and this incorporated the effect of void fraction on relative motion, isn't it? So, this we had already done. So, therefore, we find that in order to find out J21, we need to know u infinity and n. And at this point, I would like to mention that we cannot adopt a unique value of u infinity and n for the entire range of bubbly flow. Even when we say it is bubbly flow which is characterized by a more or less uniform dispersion of bubbles in a liquid medium, for all the entire range of bubble size, entire range of bubbly flow distribution, we cannot adopt a single u infinity and a single value of n. It is why, because again if you see this picture, it is quite evident that the rise velocity of this particular single bubble in an infinite medium cannot be same as the rise velocity of this particular single bubble in an infinite medium, cannot be equal to this particular single bubble in an infinite medium, is not it. So, therefore, we find that u infinity and n has to have different values in order to incorporate different ranges of the bubbly flow pattern. Now, usually we find that if suppose you plot u infinity with n, u infinity with say the bubble radius r b, then in that case you do not get a smooth curve. Okay. The curve is something of this sort, you get something of this sort, and then it rises steeper and then it falls, and then it is something of this sort. More or less this can be distributed into say 4 or 5 sort of distributions. Okay. At this RB, it is the equivalent radius, where it is the radius of a sphere which has the same volume as the bubble. Okay. So, therefore, we find out that in order to find out the pressure drop or any particular property of the bubbly flow pattern, we need to know J21. Now, J21 is a function of u infinity and alpha. Now, we find that u infinity, we will also find n, that is also a function of the bubble radius. Okay. So, therefore, we need to know either graphical or analytical expressions in order to express u infinity in terms of your some sort of a bubble parameter. Okay. It can be equivalent bubble radius or something of that sort. Now, several different correlations have been proposed for this particular condition, and we find that the correlations which have been proposed by Peebles and Garber, and this has been given in a tabular form in Wallis, this suggests the value of u infinity and n for different particular flow regimes. What they have done? They have divided the entire bubbly flow condition into 5 flow regimes. What is the first regime? In the first regime, we have very fine dispersed, well dispersed bubbles. Okay. If you find, you will find that this is the rise velocity of a single spherical bubble in an infinite medium, which we can all obtain simply from Stokes law. So, the first region, it comprises to the Stokes law sort of a region, and that is applicable for a for a very low bubble Reynolds number. Okay. Now, we find that the entire bubbly flow has been divided into 5 flow regimes on the basis of 3 dimensionless groups. The first group is the bubble Reynolds number, and the other 2 groups, they are some sort of property groups. Okay. They have been designated as G1 and G2, where G1 is nothing but G mu L to the power 4 by rho L sigma cube. G2 equals to, it is also a property group which also incorporates the equivalent bubble radius as well as the bubble rise velocity in an infinite medium. This, all these things, they are available in the book of Wallis. You can refer that, you can see it. Okay. And now, we find that based on the values of these dimensionless groups, the entire bubbly flow condition can be divided into 5 flow regimes. The first flow regime is naturally the Stokes law regime. Okay. Region 2 is when slightly larger bubbles are there, and then gradually we find that as we go into region 4 and region 5, we find that usually the region 5 expression probably is not correct here. I do not remember the region 5 expression, but most probably the region 5 expression, we have to check it, probably there was no RB in the region 5 expression, that has to be checked. This particular, the region 5 expression, please do not take it from here, this region 5 expression is not correct. As far as I remember, this region 5 expression, this is 1.53 sigma g rho L minus rho g y rho L square whole to the power half. It is something of this sort, as far as I remember. I am not very sure about it, but region 5 expression is not correct here. Region 4 and region 5, we find that the rise velocity expressions, they are independent of equivalent bubble radius, and they are a function of liquid properties only. Okay. So, therefore, here we have the terminal velocity u infinity values, and for each region the corresponding n values are also given here. So, once what you are supposed to do, suppose you are supposed to find out the bubble, suppose you are required to find out the void fraction or the pressure drop during bubbly flow pattern. First, for that you have to write down the expression of the pressure drop. There we find that alpha is important. Moment alpha becomes important, then that alpha, it has to be found out from the drift flux model. For finding out alpha, we need to find out J21. For finding out J21, we need u infinity and n. For finding out u infinity and n, you have to refer to this particular table. Now, for determining in which particular range your particular bubble lies, you have to find out the values of REB, G1 and G2. Accordingly, you select the range. Once the range is selected, you find out u infinity and n corresponding to that particular region, and then we can find out J21, we can find out alpha, we can find out the pressure gradient. Now, if you observe this closely, you find that for regions 1, 2 and 3, in order to find out u infinity, you need to know RB. What is RB? RB is the equivalent bubble radius, or the radius of the volume of a sphere which has the same volume as the bubble. Okay. So, therefore, we would next what we would have to do is, we will have to find out different methods of determining the equivalent bubble radius. How to find out the equivalent bubble radius? Now, we know one thing, that the way a bubble is formed, that depends, or rather the size of the bubble depends on the way it is formed. Bubbles can be generated by different ways. For example, we can have an orifice with its tip which is directed inside the liquid. We can introduce some gas through the orifice, and the gas comes out as individual bubbles. Or in other words, we can have a porous plate and maybe gas is introduced to the porous plate. So, it forms a blanket over the porous plate, and from this blanket the gas detaches and it comes out. Okay. We can have an agitator where a liquid gas mixture is agitated and some amount of bubbles come out. Now, the size of the bubble depends upon how the bubbles have been generated. Okay, the different ways of bubble generation and the size which we get as a result of this, I have also noted it down because they simply comprise of some particular equations. Equations come from force balances, some of the equations they are empirical equations, but all of them are available in standard textbooks, and so you need not take them down. But I will just be discussing the different methods of bubble formation and how the bubble size is determined for the different methods. For example, the most common technique is bubble formation at the orifice. Now, for this particular case we find that assuming that spherical bubbles of radius r b, they are attached to the orifice of radius r 0. Okay. So, it will be attached for a finite interval of time till the neck, it detaches at the neck and the bubble is dislodged, it rises up. Okay. Now, from force balance what do we get? If we perform a force balance in this particular case, we find that 4/3 pi r b cube into g rho l minus rho g. This will be equal to 2 pi r 0 sigma, is not it? The surface tension forces that basically helps the bubble to remain attached at the orifice, and this is equal to the buoyancy force due to which the bubble will detach and it will rise. Now, from this particular situation we find that the radius of the bubble which we obtain by blowing through this small orifice at low flow rates. Okay. This is the radius of bubble obtained by blowing through a small orifice at low flow rates. Okay. So, from this particular mass balance, if you work it out, you find this will be more or less equal to 3 sigma r 0 by 2 g into rho l minus rho g whole to the power 1/3. It simply comes from this particular equation. Okay. Now, we have observed, or rather people have reported, that instead of this particular expression, a more accurate expression is 1.0 sigma r 0 by g into rho l minus rho g. People have observed that from experimental data, a more accurate expression is this particular expression. Okay. So, therefore, we can find out R b either from this expression or from this expression, and we also find out that when orifice diameter, probably these things are already written down here, orifice diameter, if you can see, when the orifice diameter is comparable to the bubble radius, then under that condition these particular equations they cease to be valid. Okay. When will that happen? When your dB, the d0, or in other words 2r0 becomes comparable to rb. Under that condition, we find that the condition can be represented by this particular expression. Under that situation, the expression or the equation is no longer valid in this particular case. Okay. Now, we further observe that when the bubbles which are formed at a finite rate, okay, under that circumstances, the bubble radius or the bubble dimension, it depends upon a large number of other things also. For example, gas and liquid properties, details of the orifice design, the nozzle and so on and so forth. It depends upon a number of things for such particular situations. Okay. But more or less under normal circumstances, we find that the spherical bubble, the radius can be obtained from this particular expression, and it is more or less accurate under normal circumstances. So, this was for bubble formation at the orifice. Now, what is the next way of forming the bubble? It is by Taylor instability. What is this Taylor instability? This is that when there is a, just as I was telling, suppose there is a porous cylinder or a porous medium, or maybe there is a heated surface. So, over the heated surface what happens? There is a blanket of gas or a vapor which is deposited on that particular surface, and from this particular blanket gradually the bubbles they get detached and they start rising in the tube. or in the in that particular conduit. Okay. So, for such particular circumstances we find that R B can be obtained from this particular expression under this case. Okay. So, we get this is particularly important for film boiling. Okay. So, for such situations we get, or rather we can obtain R B from this expression. What is the next way of deciding? The next way of deciding is, suppose by mass transfer or by evaporation of the surrounding liquid, or maybe some amount of gas is dissolved in the liquid, due to mass transfer this amount of gas they get released from the liquid. Okay. Maybe beer, soda, etc. in this particular thing some amount of gas is dissolved, due to release of pressure this gas they get dissociated and they start rising as bubbles. Okay. Or maybe due to evaporation of the surrounding liquid some amount of bubbles are generated and they start rising. So, under such circumstances what we have? Under such circumstances we find that in this particular case the expression is in terms of equivalent diameter. So, equivalent diameter which is just large enough to break away from a horizontal surface, this is obtained from the expression here, where since the surface is important here, the beta, the contact angle in degrees is also becomes important and it is included in the expression. Right. Well, the other way in which the bubbles can be formed, this is by the influence of shear stress, as I was telling in forced convection or in mechanically agitated systems. Then under such circumstances the shear stress, it influences the size of bubbles away from the point of formation. Okay. And the size of bubbles, they are as well as the maximum bubble size which is stable in the flow, both of them they are decided by the shear stress in this particular case, and under this particular circumstances this should have been dB here. The equivalent bubble diameter can be obtained from this expression, where P by m is nothing but the mechanical power dissipated per unit mass. Okay. So, therefore, depending upon the way bubbles have been formed, we can find out dB or RB as the case may be. Usually they are formed by when any particular gas is ensuing through an orifice or some sort of a special nozzle. They can also ensue by shear stresses, or maybe when there is evaporation of the surrounding liquid, or maybe dissolution of the gas dissolved in the liquid, or maybe when the gas blanket is rising through a porous plate or during film boiling. So, whatever the case may be, depending upon the situation, we are going to find out, or rather we are going to select the accurate expression of dB. So, therefore, using that expression we can find out either the equivalent bubble diameter or the equivalent bubble radius. Please remember, the equivalent diameter is nothing but the diameter of a sphere which has the same volume as the bubble. Okay. So, therefore, once you find out there, then what we do, we go to this particular table, we use the value of RB that we have obtained, find out REB, G1, G2 from these expressions, and then decide in which particular region you are going to lie, accordingly select terminal velocities and n. Now, at this particular point I would like to tell you one particular fact. In order to find out in order to find out u infinity, what is u infinity? Velocity of a bubble in an infinite medium. But in reality, can you generate an infinite medium? For example, say a Taylor bubble, it will not be formed in an infinite medium. So, we have to perform the experiments in a confined tube. Now, whenever we are performing in a tube, due to the wall effect, the bubble will rise at a slower rate as compared to the velocity at which it would rise had it been in an infinite medium, because naturally the confining walls will try to restrict its motion, is not it? And it is observed that the rise velocity of the bubble u b by u infinity, this is a function of dB by d, where this is equivalent bubble diameter and this is diameter of the tube. Now, if you observe this particular transfer slide which I have got, we find that in region 5 the last region which we had for large inviscid bubbles. Okay. It is found that when d by d is less than 0.125, then in that case we can very well assume that the ub that we have found out that can be used as u infinity. But moment the ratio d by d keeps on increasing, the relationship between ub and u infinity they also change, and depending upon the ratio of, these are all dBs, the equivalent bubble diameter, depending upon the ratio dB by d, we will be using the appropriate expression of ub by u infinity, and then we can find out ub from the experiments, and accordingly we can find out u infinity in these particular cases. Okay. Now, this was for inviscid bubbles. Now, for viscous flow again there are different expressions for bubbles behaving as solid spheres, for bubbles behaving as fluid spheres, that means liquid rising through a liquid. For each and every case there are different expressions which we can use under this particular cases. Okay. So, therefore, this is how we find out the, or rather we use the drift flux model for the bubbly flow pattern. Now, remember, whenever we are using the drift flux model for the bubbly flow pattern, under that circumstances usually the acceleration pressure drop and the frictional pressure gradient, they are usually much less as compared to the gravitational pressure drop, in order particularly in a vertical pipe. And for finding out the gravitational pressure drop, we need to know alpha. For finding out alpha, we need to know J21, and particularly for bubbly flow, how we have found out J21 we have already discussed. Now, there are certain other important things which I would like to mention at this particular stage. Now, as I have told you, region 1, this is the Stokes region where the bubbles are perfect spheres and they rise in almost straight lines. Okay. Now, as we keep on going for higher and higher gas velocities, the bubbles start getting larger and larger. Finally, we find region 4, this particular region, the bubbles are quite large. Since they are quite large, there is a wake effect of these particular bubbles, they are very much entrapped into each other's wake, and the particular situation it appears as a more or less as a very random sort of a distribution, and therefore, the u infinity under this case it is not a function of bubble equivalent bubble radius. And region 5, it is not actually the bubbly flow pattern, it is the transition between the bubbly and the slug flow pattern. Okay. So, this you are supposed to remember, it is known as the churn turbulent bubbly flow pattern. Okay. Why it is given this particular name? It is given this particular name because the distribution resembles the churn flow regime. So, it is either the churn turbulent regime or it is named as the churn turbulent bubbly regime. Okay. In this particular situation, we find the situation which I have tried to draw in the previous slide, the situation is completely erratic and we have a large number of cap shaped bubbles, and several bubbles, and what happens, the bubble, since they are quite large, they have a good amount of wake effect and the bubbles get entrapped into each other's wake, and therefore, there is no influence of void fraction on J21, and that is why the value of n it is 0 in this particular case. Please remember this. Okay. So, therefore, regions 1 to 4 they are the different divisions of the bubbly flow pattern, while region 5 it is commonly termed as the churn turbulent bubbly regime, which is a transition between the bubbly and the slug flow pattern, where the bubbles they fall into each other's wakes. There is a wide range, wide variety of bubble sizes and shapes, and more or less the influence of void fraction, then it starts becoming less than 1 and in the limit it becomes 0. There is one more thing also which I would like to tell you. Suppose you do not make any additional efforts to control the bubble size. Under that condition, suppose you are just introducing air, Okay, there is water flowing and you are just introducing air. You make no additional efforts to control the bubble size, the bubble flow or anything. Then in that case the bubble will do whatever is best suited for it. Under that condition, depending on the flow rates, the bubble will just simply break down into a range of sizes, into a range of shapes, and they will be randomly distributed in the fluid mixture. Okay. So, and it will lie in region 5, the churn turbulent flow regime. So, therefore, in any problem, if it is not mentioned that any special effort is being made in order to control the bubble size, the gas flow rate or something of that sort, then you can very safely assume that the distribution lies in the churn turbulent regime, and accordingly you have to use the u infinity and the n, which are specifically applicable for such flow conditions. This is the thing that you are supposed to. So, when nothing is given, then you can straight away assume that the bubble or the flow pattern lies in the churn turbulent bubbly flow pattern. For other situations, we have to make some special efforts to control the bubble size, the bubble, the gas flow rate and so on and so forth. Okay. For example, suppose if we do a problem, and I will just discuss the problem here, I will be giving it to you as a home assignment, so that you can do it and we can discuss it later. Say simply in one particular vertical pipe, say it is 3 meters long and it is 5 centimeters wide, say it is 5 centimeters wide, say it is 3 meters long, and air and water are being introduced here in this particular pipe, and we know that it discharges at atmospheric pressure. This discharges at atmospheric pressure. Okay. Now, we can assume the inlet flow rates, they are given, your J L, this is given as 0.3 or 0.5 meters per second, and J G is given as 0.4 meters per second. Okay. Or in other words, this can be 0.6 meters per second, Jg can be 0.4 meters per second. Okay. So, therefore, we know that through this particular 5 centimeters diameter 3 meters long pipe, air water is introduced and they discharge at atmospheric pressure. You are required to find the inlet pressure, or in other words, you are required to find out the pressure drop across this. Once you know the pressure drop, you know the exit pressure, you can find out the inlet pressure. Now, for this particular situation, how do you propose to proceed? We see one thing, that both JL and JG, and one thing is told that you can assume bubbly flow to occur. This has been told to you. Okay. Now, how to proceed in this particular case? What do you suggest that you should do for this particular case? First thing is, moment it is written assume bubbly flow and nothing else is given, we straight away assume the churn turbulent flow regime. This is number one that we can do. Okay. Once you assume the, so therefore, since nothing is specified, first thing we do, because when you do not try to control the bubble size, they will be distributed in a wide range of sizes, and whenever there is a wide range of sizes, it will be a churn turbulent flow regime. Okay. So, the first thing that you can do is you can assume a churn turbulent flow regime. Now, moment you assume a churn turbulent flow regime, you find that u infinity, or rather u infinity, this expression is not correct which is there, u infinity can be obtained for the churn turbulent flow regime. Okay. Now, next we can find out J21, we know n equals to 0. So, therefore, u infinity into alpha is going to be your J21, okay, where your u infinity is nothing but equal to u2j in this particular case. Okay. So, what we do, first thing we do is we assume churn turbulent flow regime. Moment we assume churn turbulent flow regime, we can find out u infinity from the table, or rather from the table which is given. And we know n equals to 0. Okay. So, J21 equals to u infinity into alpha, this we already know. Okay. And again from drift flux model, what do we know? We know alpha, okay, I will write it in the next slide. We know alpha, this is equal to J2 by J into 1 minus J21 by J2. This also we know. Okay. For this J21, it is nothing but U2J into alpha. So, if we substitute this particular value of J21 here, then we find that alpha can be obtained as from this particular expression, right. So, therefore, alpha can be obtained from the expression which we have provided. U infinity equals to u 2 j, this is known, j 1 j 2 is known. So, alpha can be found out very easily. Now, what are the pressure gradients here? There is an acceleration pressure gradient, there is a frictional pressure gradient, there is a gravitational pressure gradient. Gravitational pressure gradient is very simple. Moment you know alpha, you can find it out. Okay. Your frictional pressure gradient, that also we have discussed out. The frictional pressure gradient this is nothing but 2 FTP Gj by d, isn't it? You can find out the whether it lies in the laminar or the turbulent flow regime. Usually under normal circumstances for churn turbulent bubbly regime, FTP rather it lies in the churn turbulent or in the turbulent flow regime. So, FTP can be taken in this particular form. Okay. So, therefore, and what is G equals to, this is nothing but rho 1 J 1 plus rho 2 J 2, agreed. What is J equals to J 1 plus J 2. So, therefore, this can also be found out, this can also be found out, agreed. Now, the next thing is finding out the acceleration pressure gradient. Now, one small catch I would give here. What you have to check up, it is given that its exit pressure is atmospheric pressure, you are required to find out the entry pressure. Now, you have to check whether the flow is under sonic conditions or not. If the flow is under sonic conditions, then naturally the outlet pressure of the pipe will not be the atmospheric pressure, it will be the pressure corresponding to Mach number equal to 1. Please remember this thing. These are small catches. In the midsum also I had given you a problem where the catch, or most of you could not get of the catch, but remember these things are very important. Okay. So, therefore, this you have to keep it in mind when you proceed, that the just check whether the flow corresponds to sonic flow or not, whether there is choking or not. If choking is there, for choking I will write down P exit will not be equal to P atmospheric. Okay. So, it will be P exit will correspond to MA equals to 1. So, these small things you are supposed to remember. So, what about the acceleration pressure drop? It can be obtained as G2 du2 dz plus G1 du1 dz, isn't it? This can be obtained. Okay. U1 and U2 we know very well, U1 equals to J1 by 1 minus alpha, U2 equals to J2 by alpha. Alpha and 1 minus alpha we can obtain from this particular expression. I will just discuss the problem and then you are supposed to do it and you are supposed to submit this problem. Okay. So, then accordingly we find U2, this from the substitutions, this U2 equals to J2 by alpha and this alpha we substitute this particular expression. So, therefore, we find out that U2 it is nothing but J1 plus J2 plus U2J. Similarly, U1 this is J1 into J1 plus J2 plus U2J by J1 plus U2J. Okay. Now, we find out that since the pressure is changing along the pipe, what will change? J1 is not going to change, only J2 is going to change. is not it? So, therefore, just because of J2 change there is going to be an acceleration pressure gradient in this particular case. Okay. Now, since there is no temperature change, I do not know whether I had given you the temperature, write down the temperature condition, it is around say 27 degrees centigrade. Okay. T it can be taken as 27 degrees centigrade. So, therefore, we find that under such circumstances we find that only J2 changes down the duct, nothing else changes. And what is the change of J2 in the duct? The change of J2 it occurs just because there is a pressure change in this particular case. Okay. Now, so therefore, due to J2 change what do we get? du2 dz, it is going to be dj2 dz and du1 dz, this is going to be dj2 dz j1 by j1 plus u2j. Okay. Accordingly, minus dp dz acceleration, this can be, this particular expression can be written down here. Okay. Then we can add up this acceleration expression, frictional expression, gravitational expression and get the expression of the total pressure gradient. Once we get the expression of the total pressure gradient, then from there we can find out the condition of choking, we can find out what is MA, the value of MA, verify that MA is not equal to 1, it is less than 1, and when it is less than 1 we can assume that the exit pressure is equal to the atmospheric pressure, and accordingly we can find out dp dz, and for 3 meters length we can find out P entry when P exit is atmospheric pressure. So, this is the way you are supposed to proceed for such type of problems when we apply the drift flux model to the churn turbulent bubbly flow regime. So, tomorrow we will be taking up the slug flow regime and we will find how the slug flow regime is going to be, rather how we apply the drift flux model to the slug flow regime, and if I find time we will be discussing the annular flow pattern, or else the annular flow pattern will be left as a self study for you. Thank you very much. So, you